Okay, so let's continue the talk about the previous lecture. So the main idea of that lecture was the following: that we wanted to perform separation of variables for the Laplace operator, which looks in spherical coordinates like this. So the topic is spherical functions. So the radial part is an angular part does anyone know how it looks like? Did you see the recording? Yeah. But last time we derived it, so you can watch that lecture. But I will just write the answer. Oh, sorry. Is 1 over sine of theta d in the theta and theta d u in the theta. So and there is this operator, and we want to find its eigenfunctions. So and these eigenfunctions will be called spherical functions. And to do this, we use the following trick. We took a potential that is created by the point charge located on the axis. So angles are defined like this. It's polar coordinates. So this angle is theta. It's the radius vector. And this angle between projected line is phi. X, Y, Z. So last time we took another vector R, which was pointed towards the Z direction. So E is Z times R. So the same is to write 0, 0, R. This other radius vector is our radius vector is equal to R sine theta cosine phi, R sine theta sine phi, R cosine theta. And we said that there is an expansion of 1 over absolute value of R minus R for absolute value of small r less than absolute value of big R. Well, first we can rewrite this as 1 over square root of 1 plus by the way, can you tell me the formula for this expansion, for this distance between small r and big R? So it is square root of r minus r squared. No. How does this sign appear here? Mm, but so if you want to use something, then it could be probably cosine theorem or something like this. But the straightforward idea is to write that a square of this vector is r squared minus 2 r times r scalar product plus r squared, right? And so squares of these vectors are equal to literally r squared and small r squared, right? Because hmm? Hmm? Oh, and what is their scalar product? Scalar product of these two vectors. Mm-hmm. Yes. Oh, just cosine times r times r. So yes, square root of 1 plus. Oh, sorry. R squared minus 2 r plus big R squared. And in principle, we can put sorry, cosine theta. And we can also put for simplicity r equals to 1. We can also call cosine theta equals to x. And defined an expansion of the square root, 1 over the square root. Be this sum r to the n Pn of x. So this polynomials are called Legendre polynomials. And so then the logic was the following. We know that this is a green function of our Laplace equation, so we know that the Laplace operator, which consists of, so we can actually multiply it by r squared. So r squared times the Laplace operator equals this expression. R squared times Laplacian over r minus r is 0 for absolute value of r less than 1. But it's enough. We just have this series for all r's. Because it is 0 because there are no charges in this sphere of size 1. So then we say that this expression equals to r squared radial part of the Laplacian plus angular part of the Laplacian. And we can put this under the sum. Acting on r to the n, Pn of x. This equals to 0. So, and can you tell me the value of this operator acting on Rn? So, the operator is written there. What happens when we act on Rn? Hmm? Yes, no, for one it's not true because it contains it contains the first derivative. But you can write this for arbitrary r to the n because you know how to differentiate r to the n in R. Mm, no, you have r squared to n plus n minus 1, right? Yeah, but you have r squared here, so the whole operator acts just by a number. And this number equals to n times n plus 1, right? So r to the n so is here. So this is the eigenfunction for this radial Laplacian, and if you know that all this acts by 0 and that this function does not depend on phi, we can conclude that Laplacian theta phi acting on Pn of x, which can be written explicitly in this x variable, like d in dx. Uh, 1 minus x squared d and in dx, I've changed theta to x in this expression. This equals to minus n plus 1 Pn of x. So is this argument clear? Oh, if sum of two operators acts by zero on each of these terms, because these terms are linearly independent, then each operator acts by zero. So if this part of expression is the eigenfunction of this operator with eigenvalue n plus 1, then this function should be the eigenfunction of the second term with the opposite eigenvalue. So this is the same as uh, 1 over sine theta d into theta sine squared theta 1 over sine theta d into theta Pn of cosine theta. So I simply write that 1 over sine theta d into theta is minus d into cosine theta is minus d into x. It is this transition. So see that this Legendre polynomials solve this second order eigenvalue-like equation. Is it? Is it okay? So this was the definition. You can simply expand this as a Taylor series in R and find this first Legendre polynomials, like P0 of x is 1, P1 of x is x, P2 of x is 3x squared minus 1 over 2, and so on. So this follows simply on this expansion. So this reducing these explicit values. But we also derive a more constructive expression for them. So are there any questions? So, but now let us do some upgrade of this idea. So far we studied only the set of functions that did not depend on theta. But we would like to have some trivial theta dependence. And namely, we know that all functional dependence of phi it can be split into sectors corresponding to different exponential of I am phi. In a sense, we can perform a Fourier transform in phi, and and the only functions we are interested in are of the form e to I am phi times some function of theta. Because we can first diagonalize this operator and then the whole Laplacian. So and a common eigenfunction of these two operators should have the form e to I am phi because they are eigenfunctions of d2 and d phi squared times some function of theta. So let us call them Ylm of theta and phi equal to e to I am phi times p Lm of theta. Or maybe we can write of cosine theta. So far we managed to solve this problem for n equals to 0. And the question is what to do for general m. And the idea is the following. We can take the same construction with an expansion of this distance, but go to a complex domain and choose a slightly upgraded vector R. So, namely, let us choose a complexified vector R of this form. A AI and 1. And R is as before. So it is this expression. What is the square of this vector? Well, we simply complexified everything. So what will it give us? Yes, thanks. And what is its scalar product R times R? Mm-hmm. Mm-hmm. Thanks. Uh, now we can say the same. Maybe let us add one extra index to this vector to show that it depends on A. So now we can consider the same expression. Uh, R squared Laplacian R plus delta theta phi acting on 1 over square root of R A minus R squared equals, so on one side it equals to 0, because we simply complexified this expression, and Laplace operators are perfectly defined for any analytic functions, so it doesn't matter. We don't have any complex conjugation. So on one side it is 0, but on the other side it can be expanded again as a series in R, and also in A. So we can expand it. So first we write that it is 1 over square root of 1 plus 1 minus 2 R sine theta minus, maybe better to write minus 2R cosine of theta plus A e to I phi sine of theta plus R squared. Sorry, plus small r squared. This expression. Oh, we can first expand it using this formula for Legendre, use this definition for Legendre polynomials, and this will play a role of new variable x. So this is r squared plus n r plus n theta phi. Let's use letter L here. But then we can further expand this simply as a Taylor series in A. And finally, we have this expression that sum from L equals to 0 to infinity, sum from m equals to 0 to... by the way, can we terminate the sum in m to some value? And if yes, to which value? If you try to expand them as a Taylor series. No, Legendre polynomials, because we would like to have something that depends on theta times something that depends on phi. So we should send this a to 0 and expand it as a series in A, but in reality it is A times this object. So they carry this charge. Oh, I'm calling Legendre polynomials polynomials. And what is the order of those polynomials, and how many terms of Taylor expansion will we have if we start expanding them? Well, if I try to look at the nth terms of expansion of this expression in powers of r at r goes to 0, we see that the main contribution comes from this expression. It will be r to the n times x to the n, and this r squared gives contribution to subleading terms. So the power of the degree of nth Legendre polynomials, a polynomial is n. Right? And what happens if you try to perform Taylor expansion of a polynomial? Yes, and how many terms will we have? What in the upper limit here? Yes. So other terms will vanish. So here we have this Laplace operator that can be moved inside Sn of r plus delta theta and phi r to the L, a to the m, e to n phi divided by m factorial. And m's derivative of Legendre polynomial, sine of theta. And I also forgot to write sine theta to the m's power. Which is important. Maybe better to write this derivative explicitly because it is in different notation. D m in dx d cosine theta m's p l of cosine theta, like this. And we see that again there is only one power of r. This is r to the n. So we can conclude that the eigenvalue of this angular Laplace operator acting on this function is again minus n times n plus 1. So this equals to 0. So this Laplace operator acting on e to I of phi sine theta to m again equals to minus l plus 1. And Now let us look at this operator. What happens if we take into account the action of second derivative and phi and rewrite everything else in terms of this variable x, which equals to cosine of theta. So, can you tell me the differential operator that will act on this function? So I will write this function uh, without e to m phi 1 minus x squared to m over 2, which corresponds to sine of theta to power m dm in dxm L of which is denoted by L m of x Yeah. So can you tell me the operator in X which acts on this uh, uh, function by this eigenvalue?
It's probably a Bessel function.
No, what do you mean by Bessel function?
Well, something that has spherical symmetry.
No, what do you mean? I'm asking about the differential operator. Mm, and what we are not even discussing the ideal part. Uh, in our case, my ideal part is trivial. It is simply r to the n, and it was already taken into account before. So we have this statement that an angular part of the Laplace operator acts on this function with the eigenvalue minus L plus 1. And my question is, what modifications should we do with this radial Laplacian, sorry, angular Laplacian written on this blackboard? So, what happens to each of these terms? Maybe you can start from telling one of these terms, and if it is correct, I can add it here. Oh, sorry, I wrote some m squared here, but no one asked what I meant by this. It is simply 1. Kind of made one more transformation immediately. But this was a hint. Yeah. Well, are there any terms that we have already seen? Are there any obvious terms in the The question is essentially mm, uh, how to write this operator using the coordinate cosine of theta instead of theta. What if I denote cosine of theta by x and try to express everything in terms of derivative in x using formulas like this? And also take into account that the operator d in phi uh, squared uh, acted by the known eigenvalue. So,
D on the the operator is like D on the x
hmm?
on function 1 minus x squared
Mhm.
times du on the x.
Well, u is this function. It acts on this after everything, in a sense. So it simply acts by derivative, then we multiply by this operator, and then act by another derivative.
And there is also
Mhm.
the free part is like
Mhm. Mhm.
plus minus m squared
Mhm.
divided by 1 minus x squared.
Mhm. Thank you. Yeah, that's it. So that's, I have this differential operator that acts on this on this function with a given eigenvalue. So, and the statement will be that actually all functions on the sphere can be expanded in this basis. Uh, so. Uh, uh, If we fix to uh, a given value of m, then uh, uh, all these functions PL m of x form a complete basis. The functions on this interval from -1 to 1 that correspond to values of sine. And if you combine it with theta, we will have a statement that this spherical harmonics. Mm. Which equal to e to n phi p l m of cosine theta. Form so they can form a complete basis on the sphere. And we'll prove this later. But intuitively, it should be kind of clear because we took mostly generic point inside this sphere and expanded the corresponding green function. So if you want to expand the arbitrary function, we could take its Laplacian and then try to solve the inverse equation using the green function. Since the green function can be expanded over this spherical harmonics, then the original functions could also be expanded over the spherical harmonics plus some R-dependent functions. Actually, it's a bit vague speculation because we adjusted this vector in some special way. So it was not a generic vector, but the statement itself, is a statement itself is true. Mm. And the nice thing about this is that all these functions can be expressed in terms of Legendre polynomials, simply differentiating them and multiplying by powers of 1 minus x squared to m over 2, or sine theta to the n's. And now, if there are no questions about this, I would like to tell how to get some constructive formulas for Legendre polynomials. So this formula is kind of constructive enough because you can compute the Taylor series, but you can make it even more explicit and useful. So. Yeah, and also, so we obtained this result using some indirect methods by expanding the green function. But if you look at the original problem, you see that this problem is very similar to a problem about Fourier transform, about sine functions on the interval that should satisfy boundary conditions. So this should be compared with the following problem. We have an equation d d2 u in dx squared equals to minus omega squared u with boundary conditions u of 0 equals to u of pi equals to 0. So what are the possible, well, and let us denote this omega n by, like, yeah, let us denote this omega n. So what are the possible solutions of this equation? So in general, if you forget about everything, what is the solution of such equation? Yes. But what if you care about the boundary conditions?
We need the function to vanish.
Which one? Okay. So what should we do immediately if we want to satisfy the left boundary condition? Yes. So and then one boundary condition is satisfied, but what about the next one? What about the second one? Hmm? Yes. And so. Mm, so u equals to sine of sine of nx and du, let us call it un. dun in dx squared equals to minus n squared un. So we have this discrete spectrum, and we can compare it with this eigenvalue. The difference is that here we have minus n squared, and here we have LL plus 1. And if we draw plots for these functions, so let me separate this into two parts of this story. So here we have in different pictures for P1, P0, P0, P1, P2. So this is P0, this is P1, and let us draw P2. It equals to 1 on both ends, and equals to minus 1/2 at 0. So this is minus 1. Now it is quadratic and goes like this. And this picture will look in the following way. So we have U1, U2, and U3. And so on. So one similarity that we can see here is that the number of zeros of these functions increases with the number of functions. And it is a general phenomenon that we'll prove. So it's a general property of this second order equations. So, and actually, if you compute Legendre polynomials for high enough orders, they will start looking like this. But it should be something big, maybe like 10, I don't remember precisely, and they start looking like quickly oscillating signs, but it is the typical behavior for large n. Well, are there any questions about this? So, let us then maybe let's first derive the general formula for Legendre polynomials. Maybe I can miss a spelling, but it's called something like Rodrigues formula. So we have this a definition of Pn of x as a series expansion of the square root. And to recover the single Pn, we can try to use a contour integral for around r equals to 0. So we can write that Pn of x is the integral around 0 d r to the n over r to n plus 1, 1 over square root of 1 minus 2 rx plus r squared. Did I miss something in this formula? So what should we do to this formula so that it starts giving us nth term of this expansion? So sorry. Mhm. Yes, thanks. Yes. Then all terms except the one corresponding to r to the n vanish, and the term corresponding to r to the n gives us dr over r, which equals to, so its integral equals to pi I. So this is a standard trick how to take one of the terms of a generating function. And well, now we need to compute this integral. So,
But this is a contour integral on the complex plane on a circle around x.
around 0.
Ah,
We will have a circle around. Well, let me draw it here. We will have such contour, but later. So, there is a problem with this expression, because it describes a quadratic curve. In a sense, it is not very nice to work with square roots because they have different squares. But instead, we can say that we live on the algebraic curve given by the equation y squared equals to 1 minus 2 r x plus r squared. So this is an algebraic curve, quadratic. For now it's just a notation. We can write that this integral equals to 1 or no, 2 pi I. Uh, this dr over r n plus 1 over y. But now we need to use some elementary geometry. Idea is the following. This this quadratic is a hyperbola, but it doesn't matter. This argument works the same for squares or ellipses as well. So, what I'm going to show now that this quadratic curve actually has a rational parameterization. So, the statement I'm proving now is the following: any quadratic is a rational curve. Maybe call it theorem, but it's maybe any statement is too simple to be called a theorem. Which means that it is so let's postpone this computation. Which means that it is isomorphic to CP1, which is the same as to say that there exists a rational parameterization. And a rational parameterization means that we can construct a function t, which is a function on this curve. It is a function of y and r. Maybe it was better to denote this two functions with a different color. So there are two functions. Sorry, x is a parameter. There are two functions y and r that are related by this equation, and they describe this curve. So there is a function t that depends on y and r, such that if we express them back, then y of t and r of t are rational functions. And they solve the same equation. And they satisfy the same equation, like y of t squared equals to 1 minus 2 y of t x. Hmm? Yes, thank you. Hmm, yes. R plus r of t squared. So if you ever saw all these explicit formulas for Pythagorean triples for integral solutions of a squared plus b squared equals to c squared, or something that is called maybe uh, someone substitution for computation for computations of integrals of this kind. All these phenomena come from this observation that any quadratic curve is rational. Mm. So, but now let us construct this rational parameterization explicitly. So. Uh, So geometrically, it is done like this. We have this hyperbola, and it has one point when y equals to -1 and r equals to 0. And we uh, we choose some line that passes through this point and is parameterized by its slope. Mm. So this is a line of constant slope. So under I wrote the correct definition of these coordinates. I do not forget it. So an equation of this line is uh, y plus 1 over r equals to t. So in fact, oh, sorry, not y equals to 0, y equals to -1. So all such lines pass through the same point, but with a different slope. So the question to you, how many other intersection points do we have? So how many intersections uh, mm, do this linear and quadratic function have? Hmm? No, to other points. So one intersection is here, it is fixed. Yeah, and so there is only one other intersection. Yeah. So technically, it means that if we define t like this, so it's actually this t. It's the definition of correct coordinate. So if we do like this, then to find coordinates of this second point, which will be y of t and r of t, we need to solve just a linear equation, linear system of equations. So, so because it is just a single root, we need to find one point. So the answer cannot contain any square roots, and they will be just explicit functions of t. So technically, what should we do? Uh, we should mm, Probably what is better to erase. Maybe I can erase this definition because we already have it in some form. Yes. Technically, to find this rational parameterization, we need to solve this system of equations. Our original equation of this curve, y squared equals 1 minus 2 rx plus r squared, and the line equation. So, and it's not a good idea to solve it in the class, so I did it at home, and we'll just write the corresponding formulas. So, so there is this remark. There are these formulas, and you can check indeed that this quadratic equation can be solved by these two functions. And now there is a remark about mapping of points of this curve, because our original variable was r, and we want to pass to the t variable. Uh, so r equals 0 corresponded to y equals 1, r equals 0, because we know which branch of the square root to take. It should equal to 1 when r equals to 0. So we should see where this point maps under this map. So, and what is the point that corresponds to it? So, what value of t corresponds to this point? So if you just look at this definition. Yes, thanks. So this is t equals infinity. Yes. So now there is another computation that it is not good to do in the class, but as I tried the previous times, and it is super easy to make some stupid mistake. So the computation is the following. We have this mapping between r and t, and r, y, and t. And we want to transform that expression, which we're integrating. So dr over r n plus 1, 1 over y, if you use this change of coordinates, turns into minus 1 over 2 to the n dt over t minus x to n plus 1 t squared minus 1 to the n. So it's simply a computation of derivatives of powers and so on, but it's a bit dangerous to do it in the class. So if you use this formula, then our integral can be written like this. So it is minus 1 over 2 to the n, 1 over 2 pi I, integral around infinity, dt over t minus x to n plus 1, t squared minus 1 to the n. But I don't like that it is around infinity, and I want to shrink it to x, because there are only two singularities of this function. Let me draw it like this. There is infinity, and there is this integral around infinity. I want to shrink it to x, and this changes the overall sign. So this integral becomes 1 over 2 to the n, because there was another point x somewhere. So it is 1 over 2 pi I, integral around x, dt over t minus x to n plus 1, squared minus 1 to the n. So what does it equal to? Like, not a completely explicit formula, but something that is as close as possible to an explicit expression.
Going around the point x.
Yes, there is this pole of order n plus 1. And what should we do to compute such an integral?
I can't remember how to do
But you don't.
higher power. So
But you don't need to remember this. You simply need to remember that to compute the residue of a function, you need to find its coefficient in front of 1 over t minus x in the expansion around this point. So in the expansion in powers of t minus x. So to do this, so let us consider the general case. Let us consider the integral 1 over 2 pi I integral around x. Hmm?
is the integral function as a whole over the greater than one?
No. It is a function of x, but it is a function of t, but this is also a function of t. So we have this a typical situation. Hmm? No, why? It is not a singularity. N is positive, so it is just a simple polynomial. It has singularity at infinity, but we don't care. We are computing its residue as x. So what should we do? We have this expression dt over t minus x to n plus 1 times some function of t. So of course, if we compute an integral like this, it would be 0 unless n equals to 0. But here we should also expand this function of t in powers of t minus x. So it equals to 1 over 2 pi I, integral around point x, which I do not like this, dt over t minus x to n plus 1, and oh, the full Taylor series of f from k equals 0 to infinity, t minus x to k, 1 over k factorial, f k of what point? If you write it like this. Yes. So, and now when all these functions are t independent, we can look at this full line series and compute the residue. So, and what is the term in the series that will contribute to the answer?
1 over n factorial times n to the
Mhm.
infinity of n.
Yes, thanks. So, uh, f ends of x. So it substitutes t equals x and also takes a corresponding derivative and divides by n factorial. So of course I never remember such kind of formulas. I'm always expanding it as a Taylor series and then writing the answer. So welcome. Yes, so now we can use this formula, simply substitute an explicit value of f. So, and it gives us 1 over 2 to the n, 1 over n factorial, dn in dx n x squared minus 1 to the n. So this was our computation for a Pn of x. And we have obtained this nice expression. Mm. So, do you have any questions about this? So, let us now try to look at the first spherical functions. So, maybe let us try to compute first Legendre function associated Legendre functions. So. So P0 n equals to 0, it is just 1. P1, 1 over 2, d in dx x squared minus 1, which is x, p2 of x, 1 over 2 times 2 squared, 1 over 8, d2 in dx squared, x to the fourth, minus 2x squared plus 1. So here we differentiate twice and we get 3 over 2 minus 1 half. And so on. Let us now compute associated Legendre functions. I will compute them up to some factors which are inessential. So first we have p11 of x. It equals to square root of 1 minus x squared. And that's all. We cannot take more derivatives. Then there are these functions corresponding to lower index 2. So there is p21 of x, which is up to some factor, 1 minus square root of x squared, and we differentiate this function. We need to differentiate it once. There is the definition. We need to differentiate it once, and it gives us x. And there is also another option. We can differentiate it twice and multiply by 1 minus x squared. So if we now try to write a corresponding spherical function that depends on theta and phi, what will we get? So can you tell me what this y00 of theta and phi is? Yeah. Because it's simply p0 times, well, there are no other options. It's exponential of exponential is of power 0. So then we have a little bit bigger variety of functions for L equals 1. So who is y10 of theta and phi?
Cosine of theta times e to the minus 1.
Yes. Y1, I would write them as plus minus 1 of theta and phi. What do they equal to?
theta times e to the plus or minus e and phi.
Just I phi, m equals 1. Thanks. So then y to 0 of theta and phi. What is this? Yes. No. Yes. This one. Mm. So I'm writing some of them up the overall factor, and it doesn't matter. So who is y1 plus minus 1 of theta and phi? Hmm? Sorry, 2 plus minus 1.
Minus theta times cosine theta times e to the plus minus.
Yes. Yes, and finally, who is y 2 plus minus 2 of theta and phi?
Sine square of theta times e to the plus minus 2 alpha.
Yes, so I would write it like this. Just square over this expression. And we know one state that if we multiply all these functions by corresponding powers of r, they will be killed by the Laplace operator. So let us add this powers of r in these expressions and see what we get. R squared, and here as well. So I can probably raise this computation. So let's remind polar coordinates. Z equals to cosine of theta, x equals to r sine theta cosine phi, y equals to r sine theta sine phi. And it's also useful to introduce another variable, zeta equals to x plus iy. And so what will be, what the formula of zeta will be? Can you tell this? What does it equal to in terms of spherical? Mm-hmm. Thanks. So, and now, what if you try to write all these spherical functions uh, using these coordinates of, I would say, z, zeta, zeta bar. So let me write for y to 1, 1, 1. So it should be more or less straightforward if you look at the expressions. So, mhm, mhm. Zeta, probably. Mhm, mhm, mhm. Yes. So here we should do something a little bit. Uh, so 1/2. So uh, 3/2 r squared. Well, actually, we can write this in Cartesian coordinates. It's not a problem. So it is 3/2 r squared cosine squared theta minus r squared over 2. So we can write this simply as 3/2 z squared minus 1/2 uh, x squared plus y squared plus z squared. All right. So if you write it this way, we can write that it is 1/2 2 z squared minus x squared minus y squared. Uh, and what about these two expressions? How to write them? Mm-hmm. Yes. Thanks. And so why am I asking you for this? Because using this coordinate, we can write our Laplace operator in a slightly simpler form. So this Laplace will be equal to d over dz squared. But what will we have instead of x and y derivatives? So it equals 2 in dx squared plus d 2 in dy squared, but it can also be written using the zeta variable plus 4d 2 in d zeta in the bar. So there is one expression and there is another expression. So is it now obvious that this Laplace operator kills all this? Oh, sorry, I forgot this factor of r squared, r squared, r squared. Was it obvious that this operator kills all these expressions? So it kills 1 because it contains a derivative. It kills z and zeta because it's second order differential operator. it kills this expression because second derivative of z squared is 2, and second derivative of x squared and y squared are minus 2 minus 2. Well, this is killed by Laplace, and this non-trivial form of P2 gives precisely this statement. This is also zero, although it's quadratic, because each of these derivatives contains more than can survive. It's either second derivative in z or derivative in z in zeta and zeta bar, and the same for zeta squared. So
the higher order associated Legendre polynomials will never be higher than quadratic in these variables.
hmm?
They'll never have a power higher than 2 in these new variables.
No. They contain, of course, arbitrary powers. Their power equals to L. So L equals to 0, just constant L equals to 1 linear function, L equals to 2 quadratic functions, and so on. They will be cubic, quartic, and so on. So this evaluation of this cancellation after the action of Laplacian will become less trivial, and but we have a explicit description of all these functions. So probably they're called harmonic polynomials or something like this, because they are polynomials in all these coordinates and are killed by Laplacian. So okay, any questions? Okay, then thanks for your attention.